Yet again.
Oh, no.
Yeah, change it up a little bit.
I like it.
What?
Like change.
Accumulating outside for once. Look at this. What? Lord.
What's
Are
up?
you like crazy with your desk right now? Lord, can I open a
Just
shade?
open up. Trying to get something new. Trying to find something out.
Hey, Cassie, open those windows. If this doesn't work, I can open the shade. No, just open the shade. Let those Christmas vibes come in. Are you ready after school? Yeah, and that's what I thought. This is what I found in my cereal box this morning. Found in my cereal box. So, anything to say to me?
Yeah, I'm trying to put it. Because I thought we were going to do the tunnel so she can come up, come up the hill.
Nick, should we come grab that?
Why?
No, just open the windows. I'm pretty short.
Why do you need to open the windows?
I can let them know. Christmas vibes up in here.
Okay, Jack, then stay on the desk and wrap it.
Good idea. No, you're like 8 inches taller than me.
You know that ping pong table I was eyeing this?
Yeah,
I got it.
Whatever $8 play though.
Well, you gotta pay $1 to use it. I make my money. I make my money back.
What do you do?
$1 to
Check out.
Oh my goodness.
That is kind of
Guys, we're getting out of one. Getting out of one.
Oh,
Okay, now. Jack, are you ready for today?
I'm ready. I told Seth you can't play unless you're going.
You're gonna be the first and you free ping pong tournament. You go to your house.
You seriously cannot play unless you bring it over. Because that's not fair that you buy a ping pong table and we're all going to use it.
Yeah.
That's not fair.
I mean, I gotta realize eventually you're gonna like when we graduate, I'm not gonna leave at the church.
Oh no. You just take it with.
I'm gonna take it. Exactly.
Put it in the door.
Seriously.
Put it in the door.
It's not
Hold
fair
it up.
that you
I
buy
want
it.
it. You just gotta
Take it out. Hand in the paper.
Alright.
Hold down so easily too.
Okay. Just put it on the desk again. Don't read too much into it. I'm trying to find one set that I like. So. Alright.
Word. I use Ultra Alpha for this, you know? I want to see. It took me like 15 minutes to grab one problem.
Didn't know how to type.
No, I typed it right. I did the carrots and everything else. Whatever. It took me forever.
Maybe your internet connection is bad.
Yeah, probably works.
Alright, hey, today we're gonna talk about dividing today. That's what we're gonna do today. Now, I know we have homework due, so page 312 at some point today, get that turned in. Make sure your name's on it. If you turn in later, love of God, put your name and period number on it so I know what period you're in. That's kind of the thing that makes me mad when I get it turned in later in the day, but there's no period number. I have to like search and try to figure out what period you're in. Because I don't think about that type of stuff. Alright. Okay, alright. We're gonna do division today. I want to practice, 3 or 4 different ones today to talk about division because this is going to help us when we can't actually factor things apart. Can we still find x-intercept? So that's what I want to talk about today. So in fact, we're going to start with one right off the bat that I know is factorable. I know it's factorable, but I want to show you that division actually does work for it. Does that make sense? Because I know some people, they get the idea, but they're not sure, why it works, what it goes through. Question?
Homework due by 2:30 or 3:30?
Some point today before I leave.
What time do you leave?
3:40.
Well, you got basketball.
You have basketball, so
3:40
be here, Larry.
Okay, because I forgot my graphs at home. So should I call someone right to me or should I just go home after school and bring it back?
Just take a second. Here we go. Alright, here we go. Okay, alright, so again, what we're on today, we're on section 2.4. We're going to be dividing polynomials today. So hopefully you can get kind of a handle on how this is going to work. Alright, so we're going to be dividing polynomials. The big thing today, we're using long division. So I want to make sure that you understand how this works, how we're going to do it. Now the best part is, they're already telling you what to divide by. It's not like one of those problems like you talked about yesterday, where we have to find our own roots. We'll eventually look for one of those. Okay, we'll maybe tomorrow we'll look at one of those problems. They don't give me something to divide by, I have to go find it. So we're going to do long division. Once we're through maybe 2 to 3 different examples, of different cases, how they could be easy, hard, difficult, whatever. Then we're going to switch it up, and I'm going to show you a new method of long division, which I'm betting on none of you have ever seen. I'm betting on it. Now, I know a lot of you had different ways of dividing. Like the other class said they have like a lattice or scaffolding method of division, where there's like brackets and things. I've never seen that before, but I'm going to show you a different method today. Maybe you'll like this, but it only works in one case. That's why it's kind of a rare thing. We are going to look at a new method. It's called synthetic division. Okay. All right, so we're going to talk about synthetic division. It's kind of cool. I kind of like it, but again, it only works in like one rare case. So that's why we have to know how to do long division, because this works for everything. But this is a rare case. But it will be useful later. Okay, all right. Questions about what we're going to try to attempt today? Okay, very easy. Got easy notes today. All right, so let's go through a problem. I'm going to start with a problem that I know is factorable, then we'll do a couple of problems that are definitely not. So you can see the level of difficulty here. All right, let's see. Okay, Jack, you want to read off number 17? I know that was factorable.
Parentheses. 2x squared plus x minus 10, parentheses, divided by, parentheses, x minus 2.
Okay, got it. All right. Sorry. As you're going through, I memorized those. All right. So, I know this problem is factorable. Just to prove my point that I know what the answer is going to be in the very, very end, this problem can actually split up into two things, like it'll be plus minus, because the minus sign's in the back. I'm going to go 2x and 1x, 5 and 2. And that will make the 1 in the middle, because this will be 2x squared, negative 4x, positive 5x, negative 10. So I know this is factorable. So this is the top item right on a fraction bar, and that's what I'm dividing by. So what would cancel out? Okay, so these are going to go away. So I know before I even start long dividing, this is going to be the answer. That's my other root. Okay, does that make sense? Like this one definitely works. I know that when we divide, we're going to get a remainder of 0 because of this. But I wanted to show you that. I want to show you a problem that we know is factorable for sure, so you can definitely see that it is working. Like the thing I'm showing you that it's not failing is that I'm not just making things up as we go. And I also be able to tell that way sometimes. All right. So let's take a look at this. So in the house, when we're doing long division, will be that 2x squared plus x minus 10, right? Because the dividend, that's this thing. That's the dividend. It's the first item when you're dividing. That goes in the house. All right, so dividend, and then the item that we're dividing by is the divisor. That goes on the outside. So that's the x minus 2. Okay, we good so far? Yeah. Okay. So let's jump in here. So how we talked about this yesterday is that I know there's 2 items out here, so we're going to basically work with 2 items at a time. So that's why I'm going to use 2 items here, because I have to make sure that these go underneath this. What do I have to multiply on this x to make it look identical to that? 2 and an x. That's what I have to multiply by. To make this item look exactly like this, I have to multiply by 2x. Because remember, for the variables, the powers add together when you multiply. Okay? So I'm going to multiply by a 2x. So when I do that, this is what I'm doing in my head. I'm taking a 2x times an x minus 2. That's what I'm doing. And what I'm going to do is I'm going to write that answer down right here. So what do I get when I take a 2x times an x minus 2? What do I get? I'm going to distribute.
2x squared minus 4x.
Squared minus 4x. Right? Does that make sense? Like that's what I get when I actually distribute it first. Now that I have that, when we do division, we always subtract straight down. You always subtract. That's how division works. So when I subtract, this is what's going to happen. This is going to turn out to be a negative. This is going to turn out to be a positive because when I subtract them, they change signs. Right? Because it's actually that would be a negative. That's why it turns out to be a positive. All right. So 2x squared minus 2x squared. 0. Gone. 1x plus 4x. 5x. And now what we do, we always drop down the next item. Because I always need 2. Because how many items are on the outside? 2. So I always need to make sure that there's 2 items. Okay? Alright. Now, once we're here, we drop down that item, we start all the way over again. Okay? So now, we're thinking about, okay, what do I take times this x that'll make it identical to this item. 5. Just a 5, right? So I'm going to take this times a positive 5. That's what I'm going to do. So this is what I'm doing in my head. I'm taking 5 times the x minus 2. So that's what I'm trying to figure out. How do I make it look like that? So when I do this, 5 times x, 5 times the negative 2, what do I get? 5x minus 10, right? So 5x minus 10. We draw a line. We subtract straight down. So that means I need to change the sign. So negative, positive. And when I go straight down, that makes 0. This makes 0. And we're good. So my remainder here is most definitely 0. That's my remainder. And that's what we want. That means this thing worked out perfect. That means my x minus 2 is a perfect factor. So that was an x-intercept for this problem. And the other one was this, which is what we proved. Make sense? Can you see how that works? So it does work. It's really nice how like division can give you x-intercepts. You can find if it works or not. How we know it works? The remainder has to be 0. That's how I know it works. And then whatever's left on the top, that's my quotient. This is what we call this. We call this the quotient. The answer for when you divide. That's the other x-intercept. Now, if you actually want to know what the x-intercepts are, obviously x minus 2 is one of them. So this x minus 2 represents the number positive 2. So we know we hit the x-axis there for this graph, for this one. And the other one, the 2x plus 5, you set that equal to 0, and that'll be a negative 5 halves. Okay, how I know that? 2x plus 5 equal to 0, you subtract the 5 across by 2. That's how I know that's what it would be. It's a decimal. But those are my x-intercepts for that particular graph. Okay, questions on long division so far? Okay, this is pretty quick. All right, let's do another one, but now let's make it like just a little more challenging. I know that this one was factorable. Like if it's factorable, I would never do long division. I just wouldn't. Because if it's factorable, it's easier doing this. That's why they teach you that in algebra too. But long division, it works. It does give you the right answer. So now I'm gonna pick another one that maybe just a little bit harder, just a little bit. Okay. All right. So Jack, maybe pick like something from like 5 to number 8, somewhere in that range.
Parenthesis 6x cubed plus 17x squared plus 27x plus 20 parenthesis divided by parenthesis 3x minus 1 parenthesis.
Okay. All right. Definitely hard, correct? Okay. So the weird part about this one, what makes it difficult to me, is that 3x minus 1. What we're dividing by the divisor. It's not like an x minus 2. It's not something simple. It's got a weird, odd number up front. It's fine. We can still do this problem. Hopefully it works out. We don't have to use any weird fractions or decimals or anything like that. Okay? Now, thinking back to like all the problems we've done, including this one we're about to do, what have you noticed about like the things they're giving you? Just think about that. What's something that you noticed about this? What do you notice about this?
Oh, that was actually a plus 4.
Oh, that's a plus 4?
3x plus 4.
What are you doing? You shouldn't have.
I was googling. I wanted to see if you were paying attention. Or if you memorized it like last time. I wanted to see if you
Let me pick a rate. So, all right. Is this true, or are you just making up something that's going to be impossible here?
I'm serious.
Okay. All right. So now that we have this, right? What have you noticed about the previous problems that we've done with long division and these? This one's unfactorable. That's a big thing, right? That is definitely not factorable. The reason why, if I try to like group these together, these don't have anything in common. Those definitely only have like an x squared, and I can't make this side look like that side in any way by taking no common factors. There's just no way to do that. So it's not. I can't even group it by grouping method, or factor by grouping method. Now the other thing, that was good. That was a really good observation. The second thing.
3 doesn't go into 17 or 20.
That's a big deal, right? That this is kind of weird that this 3 isn't going to go into these numbers at all. So that seems a little odd. So we know that maybe this is going to work, maybe it won't. That's something to realize. And the other thing, have I missed any terms? Like, are there any variables missing. What I mean by that, they go in descending order. Every problem I've given you so far has been in perfect descending order. Cubed, squared, x, number, x, number. They're always in descending order perfectly. I'm never missing anything. I'm never missing like, oh, I'm missing the 27x here. I have every item. That's something you need to realize. That's huge, that they're giving me every single item there. If I'm missing terms, like let's say I was missing the 27x, I actually have to fill in a 0x there. I need every single item in the correct order. I call those ghost terms. You need to fill in the zeros in there. Okay, we're gonna, hopefully the next one we're gonna pick will have one of those, so we're gonna try to look for one. Okay? All right. Questions on the setup on this problem right now. This should be a typical problem. I'm hoping this works out. I cannot guarantee that we're gonna get a remainder of 0 because of Tyler, what you just basically said. 3 doesn't go into the 20. Like this is a little concerning. This idea of the 20 here. I think we might be fine. We might be. Just because the 6 out front might save it. Because 3 goes into 6. Okay? Alright. We good so far? Alright, here we go. Long division, that 6x cubed plus 17x squared plus 27x plus 20, that goes in the house, and that 3x plus 4 goes outside. Okay, first, what do we multiply on a 3x to make it a 6x cubed? A 2x squared. Because that's what I need to multiply on that thing to make it look identical to this. Now, here comes the part we have to think about. Okay, I'm taking, and this is the part I'm doing in my head usually. 2x squared, I'm taking it times the 3x plus 4. I have to distribute that, and that's the part I do in my head. And then I have to write it down. Okay? So, 2x squared times this. 6x cubed plus 8x squared. Okay? Now we draw a line, and we have to subtract straight down. So we're going to subtract this straight down. That'll make 0. This will make 9x squared. Right? 17 minus 8. Drop the next item down, and now we start all the way over. So now, what do I take times my 3x to make this? 3x. Positive 3x, right? Positive. It's not negative, it's positive 3x. So I'm going to multiply 3x on my 3x plus 4. So when I do that, I have to distribute it, so I get a 9x squared plus 12x. Draw a line, and I have to subtract straight down, so I'm going to switch the signs here. That makes 0, this makes, what is that, 15? X. Bring down the 20. And now we start all the way over again. What do I take times the 3x to make 15x? Positive 5, right? I'm going to take a positive 5, so I'm taking 5 times the 3x plus 4, and I'm going to distribute. 15x plus 20. Draw a line, subtract straight down. 0. So it did actually work. In fact, this is my remaining roots. So if you could possibly factor that thing apart, which is not possible, but if you could, those would be my remaining roots. In fact, I would have to do quadratic equation to figure out the rest of the roots, because that's not the fact. And it's down to the square, so I can actually do quadratic equation. Okay, questions on how we divide it? Oh, good, you got lucky. That actually worked out. Do left the 1 there. Because the thing is, these could have turned out to be weird numbers like 2s and 3s, or like 2s and 4s, and 3 doesn't go into that. So we had to multiply by fractions. All right.
What did you work for?
All right. Okay. We go with that example. A little bit harder. Still worked out. Kind of nice. All right. So now, Jack, I want something that hopefully we're missing some terms, and I want something that we're going to divide by, like this. I want something that's maybe a little bit bigger. Is there one in the book that maybe has a trinomial that we're dividing by? Trinomial? Can you look up above maybe like 10, 11, 12, somewhere in that range?
This one right here is missing 3.
Oh, an x cubed, yeah. Is there one up above that we're missing some stuff? Yeah, give me number 15. let's go 15. All right, here we go. Okay, same thing. We're going to do long division. Okay, so long division, this would be hopefully my last example here for long division. Then we're going to get to kind of a different method of dividing. Because I know some of you are really good at long dividing, don't get me wrong. You're comfortable with it, but maybe not with polynomials, so I'm going to show you maybe a shortcut. Okay? Alright, on one particular case. Read it off.
18x to the fourth plus 9x cubed plus 3x squared over 3x squared plus 1.
Yeah, I didn't miss anything else. Top? It actually might be. Alright. Okay, so, first and foremost, do we notice we're missing a lot of terms? Yeah, the bottom, top is missing a bunch. It ends at x squared. We have to go all the way to a constant number. So, when we do long division, and hopefully we'll try it by factoring to see if it works. Okay, so keep that in mind. Alright, so, in the long division, right, in the house we have the 18x to the fourth, because that's the biggest term, then a 9x cubed plus a 3x squared plus 0x plus 0. I need to make sure I have every term accounted for. Every item. Now, on the outside, 3x squared plus 0x plus 1.
Do we have to add the 0 extra?
Yeah, we need to always have every item accounted for, so when we start dropping things down, they line up correctly. And I'll explain that concept here in a minute. Okay. Everyone understand the setup? Now, I'm going to get to this idea like what Cassie was asking about. Why do we need to put in zeros? It's because of the way that the variables have to line up, and we have to get the correct variable under the correct term. And I'll explain that once you see how the first one works. Okay, now, how many items are on the outside right now? 3. So that means I'm going to go with the first 3 items here. Okay, that's how it's working. Okay, so now what do I need to multiply on this 3x squared to make an 18x to the 4th? 6x squared, right? And that's going to go here. Notice, how many items was it over? 3. Because there's 3 items out here, I put it over 3 items. Because I'm going to work with the first 3 by themselves. Okay, so I'm taking the 6x squared times this thing in my head. This is usually what the part I kind of do off to the side. Okay, so I'm doing this in my head. I'm taking the 6x squared times this. So when I do this, this turns out to be 18x to the 4th. We knew that was going to work out. Now, why I need to put the 0 here? Because when I take the 6x squared times the 0x, I get 0x to the 3rd. The 0 times 6 is 0. And then the x to the 3rd is on it. And this is why I needed that 0. Because notice the variable lines up correctly. What term was it under? The 9x to the 3rd. The variables line up correctly. That's why I put in zeros. I had to have the correct variable in the correct term. And then when I take the 6x squared times 1, I get a 6x squared. It was a big deal that we had to put in zeros to make sure that the terms are lining up correctly. Okay, questions with that so far? Why did that? I need to make sure the variables like x to the 4th are lined up, x to the 3rd are lined up, x squared are lined up. And now I'm going to subtract straight down. So when I subtract, the 18s are gone. The 9 minus 0 is 9. And then 3 minus 6 is negative 3x squared. And now I need to drop down the next term. Because how many terms do I always need in this problem? I need 3, because there's 3 on the outside. So I always have to have 3. I have to make sure I'm dropping down the correct number of terms. Okay, questions, comments with how I just started that problem? I know it's different, so we have these ghost terms, as I call them. Okay, all right, let's keep going here. We're going to go to the next item. So what do we need to multiply on a 3x squared to make a 9x cubed? A positive 3x. So we have to multiply by a 3x. So I'm taking the 3x times this. Right? I'm doing this, usually I do this on the head, the side. 3x times a 3x squared is a 9x cubed. A 3x times a 0x is 0x squared. And 3x times 1 is a 3x. Now, it's division, so we draw the line, we subtract straight down. So this would be a negative, negative, and negative. And what happens, the 9s are gone. Negative 3x squared minus 0x is negative 3x squared. And 0 minus 3 is negative 3. And I draw it down the next side. I don't think this is going to work out. I think we're going to get a remainder here. So this is probably not factorable. Okay, we good so far. Haven't lost anybody yet. Okay, all right. Question?
Why didn't we take out like a 3x squared?
Begin with, you could have, technically, you could have. The problem is that what was left might not have been factorable. Maybe the numbers didn't work out. We're going to take a look at that here in a minute. See why this is not factorable. Because I always agree with you. Like the 3x squared is probably a smart thing to do to kind of look what's going to happen. I think it's because what was left here and what was going to be left in parentheses. Okay. Yeah, we'll take a look at it. All right. So we're here. Now, what do I have to take times the 3x squared to get this? A negative 1. That's a big deal. I'm multiplying by a negative 1 onto that thing. So that's why I'm going to put a negative 1 here. So when I take a negative 1 times this, I get a negative 3x squared, a 0x, because 0 times negative 1 is 0, and a negative 1 times 1 is negative 1. Draw a line. Subtracting, so that makes this positive, negative, positive, because I have to switch the signs. That's how I subtract technically. That makes 0. This makes a negative 3x. And 0 plus 1 is a plus 1. And it does look like we have a remainder. Now, how I know that's the remainder? Is there any more things that can drop down? We've already dropped everything we could. There's nothing left to drop. I've already got to the constant. We already dropped the 0 down earlier. So there's no other things I need to drop. So that's the remainder. Now, how we use the remainder, this is going to seem a little weird. I know in general math, elementary days, they usually put like R behind it. They put like remainder. They put like remainder, colon, and then you write down what your remainder was. That's fine. Okay. A lot of people do that. They put the remainder is what it is. And then what your textbook tends to do, if it doesn't do that right away, because sometimes it does, in the notes it will do that. This is how they'll write the final answer, like what the quotient was after I divided everything out. They write it like this: 6x squared plus 3x minus 1. And then for the remainder, they add on the remainder. And how they add it on, they add it like this. They make this a fraction. And I'll show you why that works. Negative 3x plus 1, that's my remainder, over what do we divide by? Like that. That's the final answer. They add on the remainder. I do want to explain that. This is one that I was hoping we'd get to one that has a remainder today. Okay, so does everyone see like the setup here? This is different, all right? We've never had one where it has a remainder. So we have a remainder, I take the remainder and I put over what we divided by. Now, reason being, let me go back to our general math question we had yesterday. Divided by 5. Is 162 divisible by 5? No. We'll have a remainder, correct? That's what we're in now. Okay, so 162 goes in the house, the 5 goes on the outside. Okay, 5 going to 16 3 times without going over. 3 times 5 is 15. I subtract 2 like I just did over there. This makes 1. I drop down the next number, which is 2. 5 goes into 12 twice. 10. Subtract to get a 2. This is what they do with remainders. Usually, like in elementary days, they always put R back here and they put the 2. But what they're going to do from now on, they make this a mixed number. It's a large 32 And what your remainder was is the fraction behind it. It's the remainder over what you divided by. That's where mixed numbers come from. A lot of people tend to forget that from like elementary days. That's why they use the remainder. It makes mixed numbers for fractions. That's where they come from. Does that make sense now? And that's what we did over there. We made whatever my remainder was the mixed number. It was the fraction behind it. Okay, questions, comments with that concept? Now I know when we have digits, I could always put a decimal here and drop zeros. Keep going. But when we have polynomials, we can't do that. We don't. It's not decimals. That's involved. It's whatever is left. Okay. Questions, comments on this idea of like mixed numbers and what we do with the remainders? Okay. I think we got 3 minutes. We're gonna do one example of synthetic division, and I think you're gonna like this. Now I can already tell you that was not gonna be practical. The reason being, if I pull up 3x squared, that was a 6, that was a 3, that was a 1. This isn't going to. It wasn't going to be practical like this because it wasn't a difference of squares. Okay. All right. Let's talk about synthetic. So Jack, give me one of those problems around. One of the problems around 17 through 20. Somewhere around there. Give me just an easier one.
Okay. Parenthesis, 5x cubed minus 6x squared plus 3x plus 11, parenthesis, divided by, parenthesis, x minus 2. Parenthesis.
All right. Okay. Are we missing any terms in this problem? No. Good. So we don't have to worry about ghost terms. If we had ghost terms, we'd pull them in. What are we dividing by? X minus 2. So you can read that x minus 2 is a very simple thing to divide by. It's a single degree item, right? What I mean by that, the highest degree is 1. Right? The highest degree is 1. It's a binomial. There's not even a number in front of the x like I just did a little bit ago. It's x minus 2. If you're ever dividing by something that is simple like that, you can do synthetic division. You don't have to do long division. And I'm going to tell you what synthetic is here in a second. It's a way to cheat long division, so it's way faster. Okay? You don't work with any of the variables. You only work with numbers, which is awesome. Okay? So here we go. Okay? So here's how this works. What number represents this as a root? Positive 2. Does everyone understand that? That would be like we're trying to check if positive 2 is a root. That's the number I'm going to use for synthetic division. I'm going to put a plus 2 right here. And I'm going to put it in a little box. I know it's simple. Okay? I'm going to draw one underneath here. Across the top, I'm going to put a bunch of numbers going this way. And then I'm going to see if you can figure out where these numbers come from. Okay, so I have a positive 2, that's what I'm dividing by. Where do those numbers come from that I put across the top? The original problem, it's all the leading numbers out front. Does everyone see that? So leading numbers, it's the leading coefficients for all my variables and the constant. Okay, this is how we do synthetic division. It's this little like process we do every single time, and the weird part is it will always give you the answer for when you long divide. It's the weirdest thing I've ever seen. Okay? All right. Drop down the first number. Just leave it alone. Okay? So you drop it straight on. So that's the 5. We're going to multiply it by the number in the box. What's the number in the box? 2. So what's 5 times 2? 10. You add straight down. So negative 6 plus 10 is 4. Multiply by the number in the box. Add straight down. Multiply by the number in the box. 22. Add straight down. I want you to put a little dashed line. What you just did there is you just did long division in like 3 seconds. Okay, you drop down the number, you multiply by the This number here is the remainder if you were to do long division. So did this problem actually work out? No, did not work out. The remainder was ugly. It was a 33. It was not going to work. It did not give me 0. In fact, all the rest of the numbers are the actual polynomial that was left that would have been left on the top of the long division bar. And all we do is we go up in power. So that was my remainder at the very end. Go up in power. So this would be just the constant. If I go up from the constant, what would be the variable on the 4? X. Go up in a power, x squared. This is what's left. I'm taking this 4 times the 2 in the box. It's always, whatever this number is, you always take it times the number in the box. We'll come back to this problem tomorrow, so somebody remember this problem.
I'll shut that thing. I sit here and I watch it.
Didn't you get
Sit
the
down
email
for
last
15
period?
seconds.
Zach, you could send out a fake email.
We're gonna have one today.
Have your dad send out an email, because
He's gone today.
I was gonna say freshmen seem to always believe him when he says this.
I did.
Oh my gosh.
Every single time.
You always do that.
I love when it does on the 17th.
Yeah, no,
Right.
then you ask him what time he said 3:25.
Grab it after you know.
I know, can you?
Brooke, I almost pulled those puppets in.
Because it's big. Look, especially if you're up there.
I would say like 0.
I think there's one very weird.
She's dead. She's dead.
Eminent domain is taking over, and I don't like it. But hey, eminent domain happens in Iowa. 180 days.
It's coming right through diagonally.
Iowa, farmland is always being taken to build new roads, and they never take it. Happens all the time. So, welcome to the government.
I wanted to cry last year. Because they're so mad. They're like, well, why don't the Indians just leave? I'm like, that's their land. Do not make them move. Why would you do that?
Technically, the whole United States is their land, so they can go anywhere they want.
They should go wherever they want. But if they're like, oh, let's go like right here. Cool, you have that. And you're on Black Hills. Have that shit. You don't pick whatever you want. Right? They're like,
Yes, it is. I don't like it.
it's like if someone came in your house and like, I want to build a nice mall right for you. We're taking your house.
Oh, you did? Yeah, she walked it. Great.
It's so good though.
Hey, that doesn't work. I blocked myself.
I
Or
did
that
it
doesn't work
too.
up here.
I didn't have to use the most confusing part.
I heard
Hey,
about,
girl.
I heard about you.
Hey.
I was doing two. I wanted to. I got
Go.
a chunk of hair.
Rock 17.